This is a production of the Chemical Education Material Study.
This is a 16-molar aqueous solution of nitric acid, formula HNO3. Watch what happens when it is poured over a leaf. Human skin behaves similarly. Clearly, nitric acid is a chemical to be treated with caution. A nitric acid molecule, as shown by this model, consists of an atom of nitrogen surrounded by 3 oxygen atoms, with a hydrogen atom attached to one of the oxygens. Nitric acid is a versatile substance. It can act as an acid, as in the manufacture of chemical fertilizers. It can act as a base, as in the manufacture of nitro compounds which are used in explosives, dyes, fuels, and drugs. It can act as an oxidizing agent, as in the etching of metals. Most chemical fertilizers contain nitrogen as an essential component. Concentrated nitric acid contains 15% nitrogen. Would it make an effective chemical fertilizer? Remember the leaf. Nitric acid is corrosive and damages plants. Nitrogen is present, but so is a strong acidity. Let's investigate this acidity using an acid-base indicator.
Here we have a set of tubes containing solutions of varying acidity, each containing methyl violet as an indicator. Note that the color varies from green to violet as the hydrogen ion concentration changes from 10 molar to 1/1000th molar. When methyl violet is placed in 16 molar nitric acid, the color indicates a very high hydrogen ion concentration, at least 10 molar. Thus, nitric acid is a very strong acid. It readily donates a proton to a base.
These models illustrate the transfer of a proton from a nitric acid molecule to a water molecule to form a nitrate ion and a hydronium ion. In concentrated nitric acid, the protons move back and forth from one molecule to another. Since neither water nor nitrate ion holds protons firmly, the solution is strongly acidic. If we are to reduce the acidity, we need to have present a stronger proton acceptor, one that is a stronger base than water or nitrate ion. This chart shows the relative strengths of certain acids and bases. We see that both nitrate ion and water are among the weak bases, with nitrate the weaker of the two.
Looking down the list for a stronger proton acceptor, preferably a base containing a high percentage of nitrogen, we find NH3, ammonia. If we add ammonia gas to concentrated nitric acid, the acidity should decrease. The safety trap would catch any backup of nitric acid. The ice bath absorbs most of the heat of the reaction. A glass tube with a porous tip is used to introduce tiny bubbles of ammonia gas into the nitric acid. The white smoke, solid ammonium nitrate, forms when gaseous ammonia and gaseous nitric acid react above the solution. The net reaction is ammonia plus nitric acid gives ammonium nitrate. But most of the reaction occurs in the solution, forming aqueous ammonium ions and nitrate ions. As more and more ammonia is introduced, the acidity continues to drop. The methyl violet changes through the intermediate colors, finally becoming violet. Let's compare our product with the known indicator colors. we see that the final solution, ammonium nitrate, has a hydrogen ion concentration of 1/1000th molar or less. Few loosely held protons are present. The acidity is low. Let's review the reaction in animation. The nitric acid is a proton donor. This time, the proton acceptor is an ammonia molecule. Proton transfer yields a nitrate ion and an ammonium ion, aqueous ammonium nitrate. The ammonium ion does not readily donate a proton to water. The proton is tightly held and the acidity is low. Repeating the neutralization in the absence of methyl violet gives a colorless solution. We use a hot plate to evaporate the water. Pure solid ammonium nitrate remains in the beaker. Ammonium nitrate is a very useful fertilizer. Its 35% nitrogen content is more than twice that of nitric acid, and when properly applied, it does not damage plants. So in making fertilizers, nitric acid acts as a strong acid, a good proton donor.
But nitric acid can also act as a base, accept a proton, split out water, and form nitronium ion, NO2+, used in making nitro compounds. Nitronium ion can react with many substances to form compounds such as nitrobenzene, nitromethane, the high-speed motor fuel, and trinitrotoluene, the high explosive called TNT. In making nitro compounds such as nitrobenzene, we start with a carefully measured amount of concentrated nitric acid. We then add a measured amount of concentrated sulfuric acid, which serves as a catalyst. The marked rise in temperature indicates a reaction is occurring. Reactions producing nitro compounds are extremely dangerous. They should be carried out only under carefully controlled conditions at low temperatures and by expert chemists. Next, we add a measured amount of benzene to the mixture. Benzene is only slightly soluble in the acid. We shake the mixture to increase contact between the immiscible layers. Yellow nitrobenzene, the desired product, collects in the upper layer.
Let's review what has taken place in the preparation of nitrobenzene. We use animated models to follow the molecular behavior. In the first step, nitric acid acts as a base, accepting a proton from sulfuric acid. The resulting complex splits out water. In the solution, we now have two ions, a hydrogen sulfate ion, HSO4-, a nitronium ion, NO2+. The third reactant, benzene, consists of a ring of 6 carbons, each bonded to a hydrogen atom. When a nitronium ion and a benzene collide, a proton transfers to a hydrogen sulfate ion. This regenerates sulfuric acid. The sulfuric acid is a catalyst in this reaction. The product, nitrobenzene, is used to make dyes and other organic compounds.
We have seen that nitric acid can act as an acid, and we have seen its action as a base. Now let's see how nitric acid can act as an oxidizing agent. Photographic etching is often done by slowly oxidizing metal plates with concentrated nitric acid. Yet the same substance, concentrated nitric acid, now containing dissolved nitrogen oxides, is often used to oxidize the fuel in rockets rapidly and vigorously. Rates can vary, yet be controlled.
Let's investigate the oxidizing power of nitric acid, which acts in such different ways. Nitric acid in water solution exists largely as hydronium and nitrate ions. In both nitric acid and the nitrate ion, the nitrogen atom has an oxidation state of +5. It can be reduced to a number of products, such as NO2, HNO2, NO, N2O, N2, NH4+, and many others. The nitrogen in these products ranges in oxidation state from +4 to -3. In most nitric acid reactions, several of these products form, but usually one reaction predominates. How do we predict which reaction will predominate and which products will result? Perhaps E0 values give us a clue.
The reduction to nitrogen gas has the greatest energy potential, the largest E0. Therefore, we might expect N2 gas to predominate as a product. Even in concentrated nitric acid solutions, comparing E0 values can be informative because the relative potentials do not vary much with concentration. Now let's try a couple of reactions with concentrated nitric acid to see what products we do get. If we add the reducing agent copper to nitric acid, we might expect to get colorless nitrogen gas. Actually, we get brown NO2 gas. Yet this reaction has the least positive reduction potential, or E0 value. Suppose we use a stronger reducing agent, zinc. Again, brown NO2 gas is obtained, and this reaction is even more vigorous. Instead of producing nitrogen, these reactions give a product of a reaction with a smaller driving force. How can we interpret this? The relation between energy potential and the reaction which dominates the system can be examined with this analogy of marbles resting on a plateau. Below are various levels to which the marbles could fall. In this case, when they fall, the marbles come to rest at the lowest level. In this analogy, each fall of a marble represents the reduction of the ions to a different product. The distance of fall is proportional to the E0 value. The greater the fall, or E0 value, the greater the driving force. Nitrogen gas is the product of the reaction with the greatest driving force. Its formation involves the greatest E0 value. Just as the marbles tend to fall to the lowest resting place, one might predict that nitrate ions would be reduced to nitrogen gas. But our experiments produced nitrogen dioxide gas rather than nitrogen.
So it is evident that while E0 values can tell us which reactions are possible, they do not enable us to predict which products will result. What other factors must be considered? Nitrate ions cannot be reduced to nitrogen gas without crossing the potential energy barrier to the reaction. Experiments show this barrier is much higher than the barrier to the reaction producing nitrogen dioxide. Thus, at low temperatures, many reactants will have enough energy to go over the lower barrier, but few will be able to cross the higher barrier. Similarly, though it is possible to reduce nitrogen dioxide gas to nitrogen gas, there is also a high barrier to this reaction. Therefore, nitrate ions will be more often reduced to nitrogen dioxide gas, even though its formation has less energy potential than the formation of nitrogen gas. The E0 values tell us that both these reactions are possible. But the availability of energy in the system, that is, the temperature, plays a major role in determining which reaction predominates. We have observed that a low temperature favors the product nitrogen dioxide gas. If we want to favor nitrogen gas as a product, a high temperature is required.
Let's consider the reactions which go on in the rocket. Rocket ignition supplies enough activation energy for some reactants to cross the high barrier. After crossing the barrier, a large additional amount of energy is released. Since the rocket chamber retains much of the energy, the temperature rises, more reactants are activated, and an extremely fast, high-temperature reaction occurs. Great quantities of hot, expanding nitrogen and other gases result in a powerful thrust. We have seen that nitric acid makes possible a wide variety of products. How is nitric acid produced?
In manufacturing nitric acid, ammonia gas and air are piped into this plant. The ammonia and air enter this reactor where they pass over a platinum catalyst. The heat of reaction keeps the catalyst red hot. Here, gaseous ammonia reacts with oxygen to form gaseous water and NO. The products from the catalytic chamber pass into these pipes. As they are cooled, NO gas reacts with oxygen to form NO2 gas. High pressures and cooling are used to increase the yield. Finally, the nitrogen dioxide is sent to this absorption column, where nitric acid forms. Let's study what is happening inside the absorption column. The NO2 gas reacts with excess oxygen and water to form nitric acid with a further release of energy. Le Chatelier's principle is applied to achieve a maximum yield of nitric acid at equilibrium. Since the reaction gives off heat, the formation of nitric acid is favored by removing heat. Cooling coils surround the column. Also, the reactants are kept at high concentration by adding excess air at the bottom of the column and water at the top. And finally, since we are forming a liquid from gases, the operation takes place at higher than atmospheric pressure.
To review, we oxidized ammonia through NO and NO2 to nitric acid. In stages, we oxidized the nitrogen atom in ammonia from 3- to 2+, to 4+, and finally to 5+, forming nitric acid. We have seen that nitric acid can act either as an acid or as a base. Acting as an acid, nitric acid donates its proton to a base and forms the nitrate ion. Acting as a base, nitric acid accepts a proton from a stronger acid, splits out water, and forms the nitronium ion. As an oxidizing agent, the nitrate ion can be used in a wide variety of oxidations. These all have favorable E0 values but vary considerably in reaction rates. Controlling the temperature helps control the product. The application of Le Chatelier's principle allows control of the equilibrium yield. Through a knowledge of fundamental principles, we can understand and control the complex processes in which we produce and use nitric acid.